When you start working with deep learning, it is easy to assume that writing the actual neural network code is the hardest part of the process. But the real danger lies in silent failures within your training pipeline. You can easily build a system that outputs complete garbage without ever throwing a single visible error message. To prevent this, we are going to build a mathematically sound training pipeline from scratch. We will walk through 5 strict checkpoints: data preparation, code isolation, mathematical verification, baseline training, and systematic scaling. Nailing down this rigid sequence is what separates a model that merely works in a controlled tutorial from one that survives the demands of a real-world production environment. Step 1 happens before you write a single line of code. You need to spend hours manually inspecting your raw dataset. Check the class balance, look for extreme outliers, and determine the visual scale required to distinguish objects. During this phase, you might consider augmenting your data. Mirroring an image is a standard trick to double training volume without extra work, because the mirror image of a human face is still a valid face. But you have to know your specific data to avoid traps. Classifying asymmetrical objects, like specific Lego pieces, means blind mirroring will corrupt your dataset. Flipping a left wing physically changes it into a right wing, placing it in an entirely different class. Once you understand your data structure, clean out any duplicates and systematically shuffle the dataset. Raw data often arrives grouped by class, and feeding sequentially ordered data into your model will derail the training process. Next, split that shuffled data into your training and validation sets. But here is a critical rule. You must never shuffle your validation data once it is split. You calculate your training loss in randomized, chunked mini-batches. Keeping your validation set entirely static ensures you calculate loss consistently across the same set of images every time. This gives you a true benchmark of the model's progress. Skip this manual inspection or split the data incorrectly, and your model will simply memorize the dataset's structural biases instead of learning the visual features you actually care about. Now we test the code pipeline itself. To do this, swap in a dummy neural network with just a few layers and strictly disable all data augmentation. Deep learning involves intentional randomness, from weight initialization to dropout. You must set specific random seeds in your code so that your results are reproducible, and any bugs can be consistently triggered and tracked. With a static seed, we can mathematically verify our initialization. If you have n classes, your starting loss with randomized weights should equal exactly negative log of 1 divided by n. Check your cross-entropy output. If the loss starts anywhere else, your math is wrong. Next, run a bogus data check. Force all your input images to render as solid black squares. Your validation error should immediately spike, proving that your network is actually reading the input images to make predictions. There is one extremely common error that will pass those initial tests: accidentally mixing up the batch dimensions with the channel dimensions when writing your vectorized tensor code. To catch this, we force the loss to depend entirely on a single output and backpropagate the gradient to the input layer. If properly isolated, you will see a non-zero gradient on that single input image and a zero gradient everywhere else. Passing these mathematical and dimensional checks guarantees your foundation is clean. Any errors you encounter later will be architectural flaws in your model, not invisible bugs in your pipeline. With the pipeline secured, initialize a standard pre-trained architecture like ResNet. Even if your target domain is highly specific, like medical imagery, pre-trained weights will save you months of computational time compared to building from scratch. Lock in your baseline optimizer defaults. Select Atom. Set a constant learning rate between 10 to the negative 3 and 10 to the negative 4, and leave learning rate decay turned off. Actively disable every form of regularization. Remove L1, L2, and max norm penalties from your loss function, and ensure dropout is completely disabled. This shows what we want to see next: an unregularized model completely overfitting a single batch of training data. We are looking for the training loss to crash directly into zero, proving the network has enough capacity to learn. Achieving 100% accuracy on a tiny batch confirms the network has the mathematical capacity to solve the problem before adding constraints. Now we fix that intentional overfitting. Add batch normalization back into your layers and begin a random search protocol to tune your hyperparameters. Effective optimization depends on rigorous tracking. You must log every result and change only a single hyperparameter or data source at a time. If you increase the size of your training data and tweak the architecture simultaneously, you create a tangled experiment. You have no idea which specific factor caused a jump in accuracy, or if one change degraded performance while the other compensated. When scaling this process, do not fall into the multi-GPU trap. Spanning a single model across multiple GPUs yields heavy diminishing returns because of the communication overhead between the hardware. The mathematically optimal way to use that compute power is to launch completely separate parallel experiments on each distinct GPU. You evaluate multiple independent hyperparameters at once, exponentially accelerating your discovery phase. We started by scrutinizing the raw data to remove structural biases, locked down a reproducible code environment, proved our math was sound, and verified the model's sheer capacity to learn. This verification process creates a predictable framework, shielding the project from the silent failures that typically stall development. Take this bulletproof framework, swap in your custom datasets, and confidently launch your own parallel hyperparameter experiments. Possessing this verified, mathematically sound pipeline is the final required milestone before your machine learning model can safely graduate from the lab into live production.